Okay. Okay. So um, if there are any problems, please let me know, and or let your colleagues know in class so that we can fix them. But let me start by introducing myself. So I'm a researcher here at DIAG, and my main research interests are related to reinforcement learning and robotics. And this course will be about probabilistic reasoning and reinforcement learning. So what I will try to do in this first minutes of class is trying to get you excited about this topic and trying to bring you some interest in this so that you will be not so sad when you will see all the formulas and whatever it's needed. um, okay, actually, this is the wrong one. Give me just a second. Again. Audio is muted on Zoom. Uh, it's not, right? Shouldn't be muted. I don't know why you're saying so. It's so complicated. This is the PDF. This is the right slide. Okay. Why it's open the other one? Okay, cool. So let's see what happens here. You will see an impala that is trying to learn to work. Uh, these animals are quite interesting because they learn to walk few hours after being born. And you will see that this impala, maybe you don't see it a lot. The slides, this is better maybe. You will see that the impala tries to walk a few times, it falls, and it will retry again and again and again until it will succeed. So what is happening here is that the impala is getting, is learning in a similar way to what we'll try to study, which is learning by a reinforce. So the reinforce here is the fact that the impala walks. So it's getting a positive signal when the walk is being successful and a negative signal when it falls, right? So you will see that now the impala is at least learning to stand and making few steps. And eventually it falls again, but it's improving. You see that it's progressing real quick. Actually, I wonder whether you can see correctly the video here. I can optimize for stream. If there is this option, I don't see the option. So that's it. Cool. So this is the overall idea, what actually we'll try to do. Of course, you will not see learning your agent or computer or robot so quickly. It will take a lot of time to converge and reach some capabilities like this differently from what you see in animals. But still, this is the overall idea. Now, I selected this video from YouTube because I find it very clear to give you an understanding of what reinforcement learning is. So I wonder whether you can hear it. No? You can't hear it. Give me a second. I'll try to. This is.
means time for baby to speak. Maybe.
Wait. What can I do? Yes. Uh, uh, um, no. I think the audio thing is impossible uh, because you're not getting my computer audio anyway uh, for some reason. And I selected as a source here microphone, same as system, but this is not probably what we need to use. Audio settings. more. Here, maybe. So let's go back. Let's go back on mute here. Here.
Okay, baby. Time for Baba to sleep, which means time for baby to sleep. Maybe a bedtime story? How about reinforcement learning? Say Baba wants to teach his Roomba how to cross the room. The robot needs to get from one end of the room to the other really fast. It can just meander around and finally get to the other side like it normally does. But if we start to score how well it did, then using reinforcement learning, it can learn to go faster. Think of the Roomba instead as a mouse. We'll call him Mousy. Mousy is in a maze that looks just like the room. And on the other end, there's some nice stinky cheese, Mousy's favorite. Mousy wants to get to the cheese fast so he can eat it, but he doesn't know the best way to get to the cheese. It can start just like the Roomba, just meandering around until it sees the cheese. When he's done, we can rate his attempt and give him a score. If he wastes too much time or goes back to where he came from, we give him a small score, and Mousy learns to avoid doing the things that he did that time. If he gets straight to the point and gets to the cheese fast, we give a large score, and Mousy gets more encouraged about the things that he did. Now, Mousy has a terrible memory, so it takes him a long time to learn. Sometimes he just meanders around too to explore, but eventually he learns. And that is exactly what reinforcement learning is. The robot is just like Mousy. We tell it to do something, and then rate what it did when it finishes. Maybe give it a low score if it takes too long to get to the end. And it slowly will learn to avoid those paths. Kind of like how babies learn too, but only if they listen to their baba. Alright, come on, baby. Let's put you to bed. Do you want another story? Um,
Okay, now we should be back to normal audio. Uh, okay, so this is the overall idea.
how about
Now let's see what reinforcement learning can be used for. So this is, I'll basically be growing in difficulty of what you are seeing. This is an Atari game, Breakout. You probably have played this game. And you can see a reinforcement learning agent who is controlling the paddle here that it's learning to play. Actually, the video started after at 100 training episodes, and the number of episodes have been growing. And you have seen that the agent has been improving over time, uh, up to this point where it learns that it can send the ball to the corner and stay above the bricks so that it can break all of them. So this is learned uh, by the reinforcement learning agent through experience as the animal that we have seen, the impala that we have seen does, and by trial and error. Uh, so by the end of this course, you will be at least able to do something like that. And this is at least because you will be probably choosing your projects also on games, but also on some locomotion tasks for simulated robots and stuff like this. So, but let's grow in complexity here. Let's switch to something that might get you a bit more excited. And let's watch this video, which has been produced by OpenAI. OpenAI is a company that is working actively on reinforcement learning, and actually You will be using some of the code that they released over time, which is OpenAI Gym, that provides an interface to Atari video games and some robotic simulations exactly to perform reinforcement learning. Um, so I'll let the video talk, and I'll mute myself here. And
On Earth, the simple rules of natural selection and competition led to the evolution of increasingly intelligent life forms. Today, we ask if comparably simple rules and multi-agent competition can also lead to intelligent behavior in a new virtual world. These agents are playing hide and seek. These agents have just begun learning, but they've already learned to chase and run away. This is a hard world for a hider who has only learned to flee. However, after training in millions of rounds of hide and seek, the hiders find a solution. The hiders learn to use rudimentary tools to their advantage. By grabbing and locking these blocks, they can create their own shelter. The seekers are locked in place for a brief period at the start of the game, giving hiders a chance to prepare. Even so, the hiders must learn to collaborate, accomplishing tasks that would be impossible for any single individual. The hiders are not the only ones who can learn to use tools. After many generations of failing to break into the shelter, the seekers learn to jump over obstacles using ramps. However, after many millions of rounds of having their shelter breached, the hiders learn to take away the primary tool the seekers have at their disposal. Note that we did not explicitly incentivize any of these behaviors. As each team learns a new skill, it implicitly changes the challenges the other team faces, creating a new pressure to adapt. We've also put these agents into a more open-ended environment, randomizing the objects, team sizes, and walls. In this world, they learn to construct their own shelter from scratch, requiring that they arrange multiple objects into precise structures. To prevent seekers from using the ramps, the hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy that the agents learn. However, we found that after more training, the seekers discovered that they can jump on top of boxes and surf them to the hider's shelter. In the last stage of emergent strategy that we observe, the hiders learn to lock as many boxes as they can before constructing their fort in order to defend against box surfing. So how do agents acquire these skills? They're trained using reinforcement learning, an algorithm inspired by the way animals on Earth learn. The agents play thousands of rounds of hide and seek in parallel for many days. They train against each other as well as past versions of themselves using an algorithm called self-play. Coevolution and competition on Earth led to the only generally intelligent species known to date, humans. While this world is far less complex than Earth, we have found evidence that simple rules can lead to increasingly intelligent behavior from multi-agent interaction.
okay. Um, so
Much larger and more diverse environment, truly complex and intelligent agents. On Earth, the simple rules of
okay, it stopped. Um, cool. So what happened here? The researchers at OpenAI created a simulation with these red and blue agents that are just, I mean, you can think of them as agents in a video game, okay? So they created these agents was only goal, so they got the only information that they got was, did I succeed in hiding or did I succeed in finding the other character? So they placed them in this environment where they had these tools, which were, as you have seen, the boxes, the walls, and so on and so forth. And they uh, let them train just by using this information. So what does it mean, train, in this case? They let them act in this world and see whether they got any positive information, which is succeeding, or any negative information, which is failing in hiding or finding the other character. Um, and after, as they mentioned, million and million of training steps, so million and million of times that this whole thing starts from scratch and ends with an information for the agent being success or failure. They finally got that behavior, and also, as you have seen in this simulation, they found out some, I don't know, that they could surf on the boxes. That is something that you wouldn't expect. I've seen one phase that was saying, what the hell is happening here? Uh, in fact, they also learned to exploit a simulation bug that is not shown in this video, but in another video, that basically allows them to just jump from one area to the other of the of the room where they are playing. Let's see some other cool results that might um, get you excited about this topic and what you can do with this, with reinforcement learning. Let me unmute here. Mute here. And wonder whether this is easy. So mute myself here.
Dota is one of the most popular and challenging competitive video games ever. Playing Dota means you have to coordinate and focus as a team of 5. Last year, we built a bot that defeated the world's best players at the 1v1 minigame. This year, we want to beat the best pro teams at the full game. To do this, we've built a new AI system, which we spent the last few months training. It uses reinforcement learning at a much larger scale to train our bots to play together as a team. We're now starting to play against amateur teams to test our skill. And to our surprise, so far, we've won our first games against every team we've tested.
Didn't.
What?
You have ult?
Yeah, but it's gonna kill you too. Someone else TP got him. I tried. I got control to come out. Everyone TP. Everyone TP. Everyone TP. Get this guy. I can't even.
But to figure out how good our bots really are, we asked a Dota expert to take a look.
My name is William Lee, better known in the Dota community as Blitz. Blitz here with Chrissy. Just going to give a brief explanation of the game for people that don't know about the game. Rules are very simple. It's kill the enemy team, take the buildings. Every hero has a variety of unique spells. They'll be playing a mirror mode where both teams have the exact same heroes.
Here, the human team is dealing significant damage to the baseless 5, and Crystal Maiden comes in to defend the barracks. She jumps in with Blink Dagger and shields herself with Black King Bar, while channeling Freezing Field to deal massive amounts of damage while being uninterruptible. Due to her combo, she ends up taking out 4 human players in a 2v5 fight.
Oh, wow.
Yeah.
Well, that's it.
Oh man. GG.
And GG's called. Good game. Humans no longer think they can win. They would be absolutely correct. So their dev team got absolutely crushed. I think it was the fastest casting gig of my life. Then it went into game number 2. The humans kind of, I mean, they had time to like think about the game and stuff like that. They got crushed even harder. And the bots did exactly what I hoped for, is they own this area of the map. You take away 2/3 of the map. They didn't even touch these 2 bottom towers, and they would be 100% correct in this. This is like one of the highest level plays that you can make. This side of the map is incredibly hard for the bots to control, and so they're just playing this top side and this mid side, because they understand that these are the 2 most important parts to control in the game. The ability to like intuitively do this is insane. Doing it 1 game, I could maybe chalk it up to just dumb luck. Doing it 2 games in a row, flipping the sides, means that it's more than just coincidence. It took me, and I'm fairly reasonably good at the game, 8 years before I learned some of the strategies. I would say it was pretty easy to quantify for me. It was about 8 years for me to learn the strategies that the bot was intuitively doing
To train our bots, we use reinforcement learning, self-play. We run the game on over 100,000 CPUs, and our bots learn from every game they play. Because Dota is so complex to learn, even for a single player, we created a hyperparameter, which we call team spirit. The 5 bots start out completely selfish, but tuning this knob tells them to care about their teammates, so that they can learn to play together as one unit. After seeing the bots win against the test team, Blitz wanted to challenge it himself. He has a higher rating than the test team, and we paired him up with the best players in our audience.
And so we can see Blitz is about to die here.
Blitz is definitely dead. Yes.
And so now the humans are in trouble. 2 of the team members are dead with 20 seconds remaining, and the bots are about to take their first lane of racks. Another big fight happening here with the bots actually winning.
The game, at first, started to go to the humans. But eventually, our bot managed to beat the stronger team as well. We're still far away from beating pro teams, but I think everyone here was surprised to see this.
I think the team fight aspect of the bot was excellent. Like, it didn't mess up. When it came to coordination, it was some of the best, like, just pure team fighting, because it felt like I was just getting, like, hammered every single time that I made a mistake, and I feel like normal humans don't do that.
The Dota World Championships will take place in August. While the best players in the world are getting ready to compete, we're also working on the next version of our bot. To see how far we've come, we'll host a live match in July, where we'll play a team of top players.
Okay, I'm sorry for the noise. But I'm muted here, and I don't know where the noise is coming from. Also because this computer is muted, and this is not, but it's using only the computer audio in theory. So I don't know why it's making that noise. But anyway, I think you got the idea also here, right? I don't know if you ever played Dota. Many people do. And what they did is creating a team of bots that is actually capable of winning against some good players at this game. So it's not beating me that I'm completely useless at this game, but they're competing against professional players. And you'll see that this has been done in several domains, one of which has made the news a lot, which is the one that I'm going to show now.
Its name is AlphaGo. It was made by Google's DeepMind.
Okay. The one that I'm going to talk about now has made the news a lot because after chess, right, the next big game to beat a human, to have a computer beating a human at, was Go. So Go is a Chinese game, a Chinese board game, where you have a huge number of possible states, right, of possible combinations in the board that it's basically impossible to do any hard research where you try all the possible options. So in this case, another company, DeepMind, which is owned by Google, has developed an artificial intelligence agent, specifically a reinforcement learning agent, that has been capable of beating a human, the top player, the top human player in the world at this game. Now, why this was a big deal? It's because I mean, they thought we were far away still from that result. And so this came earlier than expected using reinforcement learning and neural networks. Also what you have seen before in Dota and in the hide and seek domain, It's a combination of neural networks and reinforcement learning. Okay? So now I'll try again with the audio here to mute. Unmute. Actually, let me try to see whether you can hear the audio, even if I'm.
Division. The AlphaGo AI algorithm beat a human at the world's hardest game. This is a historic moment in computer science and artificial intelligence. So what exactly is Google DeepMind? Where did it come from? And what can the company's artificial intelligence actually do? In this video, we'll find out.
A computer program beat a human brain at the ancient Chinese board game of Go. The final score 4-1, a triumph for artificial intelligence equipped with human intuition.
The victory of a program over a human in the ancient board game Go has sparked intrigue and, in some cases, concern. It shows that a machine has approximated human intuition and outsmarted the best human brain in the game. It's something that scientists hadn't expected to happen for at least another decade, and it's a giant leap for artificial intelligence, showing that machines can learn on their own.
I think maybe the game ended.
No, I don't think so, because it looks like Yi is still counting.
No, I think he resigned.
Wow, I think you're right. Wow. Wow.
This was the moment a computer called AlphaGo beat a master of the ancient Chinese game Go. It's not the first time a grandmaster's been humbled by a machine. But what makes AlphaGo different is that it's the first demonstration that machines can truly learn and think in a human way. AlphaGo's victory shocked experts in the artificial intelligence community. Many thought such an event was at least a decade away.
So firstly, a few questions. Why is this important and what's all the fuss? AlphaGo shows that machines can really learn. How so? Well, instead of using brute force to calculate all the moves it could make like previous AIs, AlphaGo used reinforcement learning and neural networks to mimic the learning process of a human brain.
Okay, so I found out the way to avoid the noise in the room. And again, they talk about intuition in this video. It's not really intuition. It's nice to think that way for like machine learning AI engineers or researchers. But that's something that we'll see what it is actually. It's called the value function that can be thought as an approximation of some intuition, but it's just a utility function, something that says how good some actions are if you execute them from a certain state. Okay, so it's not intuition, but it gives the idea to outsiders from this world. Now, all of this, you may think, works only in simulation, so you can do these cool things only with video games and all of that, but it's actually not true. And you can make very cool things also, you can do very cool things also on robots. Here, I'll not turn on the audio for the public at home because it's useless. You just will be interested in the video itself. Let me start it. So at Stanford, fly. Also, So I will repeat what I said. Is that here, I mean, as you have seen, this has been a video showing acrobatic maneuvers done by a robotic helicopter. So a robotic helicopter means nothing else than a helicopter controlled by a computer, like autonomous cars, autonomous helicopter. These are considered robots just because there is a computer brain inside them. This has been trained using reinforcement learning. And what I've mentioned is that the training has not happened directly on the robot here, because why? Because we said in reinforcement learning, like the impala that is learning to walk, we need to do trial and error. So we need to fall, we need to try again, and so on and so forth. And in this case, falling means destroying the robot, and you don't want to do that. Instead, there is basically no cost in destroying a character in a simulation, because you can restart the simulation and you're done. Here, you need to replace all the hardware with a high cost. Okay, so typically when you do reinforcement learning on robots, you start training in simulation, and then you might refine your behavior directly on a robot when you know that you are in a safe setting, or at least that your behavior is reasonably safe. Okay, this is this is another video that I'm going to show you, and this is basically the last one. And then we're going to switch to some actual content, hoping that this interested you and motivated you to go deep in this topic. So let me mute. Actually, before muting, this video is, again, locomotion on a simulated sort of robot. It's not really a robot, it's a simplified robot. And you will see the behaviors that the agent has learned by just obtaining a positive signal from how much forward it was moving. Okay, so the progress in moving forward. So that's the only information that the agent got, except being placed in this environment and being instructed to execute the walking behavior. So they placed this agent in the environment, they created different environments, they say to the agent walk, and the only information that the agent was getting after that was, did I walk more than before or not, basically. So let me mute again. So just for your you that you're on the remote side, there is no audio in this video. I forgot, so I can just talk through this. So you can see that this agent has been learned to move forward, and there was no instruction being given on jumping and other things like this. So the agent learned to jump just because it was the only way for it to pass the wall, as well as to pass these holes without falling down. And so progressing in the walking situation. So this has been done on several robots, if we want to call them this way. And they're modeled as robots in the sense that they are controlling the joints of the robots. So that's appropriate as a simulation. Okay, so you will see here some other agents learning to walk, that learn to walk. Let me jump to the end, which is probably more interesting here, the human. So you can see that the human at this point has not learned yet to go through walls and it falls down. After some more training, it learns that a good locomotion pattern for him is to move the arm in order to get some momentum, basically. It's, I mean, it's not the best locomotion, but it's sort of reasonable. Um, and actually, in your projects, you will be able to choose also something related to locomotion or humanoids like this, and like the other one, the ant, that you have seen, and other sort of simulated agents of this kind. Now you can see that the red arrow here shows that somebody that is basically pushing the human in order to let it fall. But it learned to not fall, and eventually it learns to not go in face of the wall. So we can declare success in this sense. So the end here should show you the final behavior of the agent running through the walls, if I'm not mistaken. Yeah, it learned. It's not bad in the end. Okay. So here I'm already unmuted and I can talk. So what is the overall schema? What we have seen in all these videos is always the same. You have a reinforcement learning agent, which is your character, your robot, or whatever, the brain of your machinery that you're trying to control. And the only thing that this agent gets is experience. Experience in what form? In the form of observing a state, a situation in the world, in the environment, or in the simulation, and it takes some action given this state. This action has an effect in the environment, in the world. Of course, this effect is not controlled directly by the agent. The only control that the agent has is the action. Okay, and from this, the agent gets back a reward, which is the signal that I was talking about before. So the reward is the information: did I perform well in the task or not? Okay, am I doing well or not? And also a new state, of course, as an effect of executing an action, you get a new state. So let's say I'm the agent, I am in this state, my task is moving forward. I'll take a step forward, I'll get a new state, which is being in this place and getting a positive reward because I moved forward. Now I try another action, which is I will move here. I get a new state, which is being here, but I will get 0 or a negative reward because I didn't move forward. Okay. So this is the overall schema that gives you the idea of what you are going to play with. Now, more motivation to study reinforcement learning. You can use these algorithms, field of research, or whatever you want to call that, because it includes all of them, to do cool things, as you have seen. There are many interesting things that you can do. It's fun because I mean, of course, you have seen some fun results. Another positive outcome of this is that there are good jobs out there in reinforcement learning. As you have seen, there are several companies working on specifically on reinforcement learning, not only on machine learning, but specifically on reinforcement learning. Just to name a few of them, we have OpenAI that you have seen, you have DeepMind that you have seen in so Google, basically. You have Sony that is working in this field, and few other big names. that can give you very good jobs and with satisfactory salaries too. Uh, the other thing is for those of you who are interested in not only doing things, but also solving new problems and new challenges, there are lots of open problems there. So if you want to do research, this is a very good topic to do research in because there is a lot of stuff to be done. This is the right computer. So this said, what are the ingredients that we need now to study reinforcement learning? I'll go from the closest thing to reinforcement learning to the most far away, which is, first of all, an understanding of the utility maximization theory. So utility will come from seeing the rewards that you get and try to maximize them over time, okay? And in order to do this, you need to also understand how transition functions work. What is a transition function? Is the function that makes me evolve in the simulation, in the environment, or in the world, however you want to call that. So if I take an action, I will be in a new state, and this is a transition, okay? And these, in fact, are nothing else than probabilistic temporal models, because the word is stochastic and it's not deterministic. Why? Because if you give an action to your robot, you have some probability of ending up in a certain state that is actually forward, but some other also moving a bit on the side because there is noise in the actuators, in the motors, and so on and so forth. And in order to learn probabilistic temporal models, you need to understand probabilistic models and starting from probability. So what we'll do is we'll cover, first of all, today, just a very short, and I didn't want to do that on the theory lessons on YouTube just because this is just a recap. It's not really new theory. You can watch this video anytime also on YouTube because it's being streamed there and it will be there. So we'll do a basic recap of probability theory. Then we'll do probabilistic reasoning, not over time and over time. This will be the first few lessons. Then we'll talk about decision making and Markov decision processes that basically are Markov decision processes are the tool that we're going to use in order to do reinforcement learning. It's the formalism that over which reinforcement learning is based and run. And then we're going to talk about reinforcement learning, name few algorithms, try to look at some papers in class with me. So the theory will be mostly done again on YouTube, offline, and looking at the papers, going a bit deeper in some topics, looking also some implementations will be done in class here, together with answering some questions. Speaking about questions, if you have questions, please post them on Slido, and I'm going to check now if there is anything. There is nothing yet. But if you have them, please just shoot them there, and I'm going to answer those. As I've mentioned in the document that I've created, I've been looking at the Zoom chat because I was in front of the computer, but normally I'm here, so I don't see necessarily what is written there. So just use Slido for any important thing. Oh, of course, who's in class? Raise your hand and ask the question. Okay, so let's move ahead with this probability recap that I expect to be nothing new for all of you. I guess everybody has studied some probability theory here. So just really something quick. So the question is, if I leave for the airport 60 minutes before the flight, will I arrive on time? What is the answer? Is it yes? Is it no? What is the answer? It's maybe, right? What does it mean maybe here? It means that in our world we have few problems that unfortunately we cannot fix, which are the partial observability. We don't know what is the state of the world. So we don't have full information. We don't know the road state, the traffic, and all of this stuff. we have noisy sensors, meaning that we can have traffic reports, but those are not perfect. Actually, they are imperfect. So this is, for us, the traffic report is a sensor because it gives us the information about the word, but it's noisy. There is action uncertainty because even if I drive to the airport, my tires could be flat. I could have to stop to get the gas for the car, and so on and so forth. So there is uncertainty also in the action. And all in all, the world is complex, and we cannot reduce complexity. So the answer to this question is maybe. And this translates mathematically to something like, I will get at the airport on time with probability 0.2. This is not really something that we can compute unless we make a lot of assumptions, but it's just to give you an idea. So let's get our dictionary for the next few lessons. So here I named some words that you need to recall. So big omega is our sample space. So if you look at this image, the sample space is nothing else than all the possible outcomes of rolling a die. Okay? Now, small omega that belongs to the sample space is just one sample point or event of this sample space being this one specific outcome, okay? Of course, the probability of, the probability of each event must be a probability, and this means that the probability of all the events must sum to 1, and that the probability of a single event is above 0 and smaller or equal to 1. What is an event instead is just a subset of omega, so for big omega. So for example, in this case, the probability that the outcome of a die or rolling a die is greater than 4. So we can compute this stuff. So what is the probability of a certain event? Or actually all the events, in this case, have the same probability, which is 1/6. And what is the probability of rolling a die with an outcome which is greater than 4 is just the sum of the probabilities of 5 and 6, which is so 1/3. So 2/6, 1/3. Something more is that you need to recall is what is a random variable. So a random variable is just a variable that has basically outcomes that are numerical, discrete or continuous, either discrete or continuous, and they represent some random phenomenon. Like, for example, the outcome of rolling a die is a random variable. A probability distribution of a discrete random variable is nothing else than a list of probabilities associated to all the possible values that you can get in this discrete domain. And of course, this sums to 1. So again, here, an example, the rolling a die, the random variable here is that it's actually odd. So this is a random variable. So the outcome of rolling a die is odd. This is our random variable. And this can have two values that are discrete, which are true and false. Other discrete random variables can be the weather that we can discretize in sunny, rainy, cloudy, snowy. And also continued random variables here can be, for example, the temperature. The temperature can have any value. So this is basically how this translates to some plots. So these are all the possible values that your random variable can have, and these are the probabilities. Here they are not really in a probability term, but you can normalize this, and this becomes a probability, okay? And same here for the continuous case. Now, some more notation. We will use capitalize letters to represent random variables. Like, so the probability of capital cavity is a random variable, and this can have values true and false. Um, then we can have the probability of cavity being true, or also this being written as probability of lower, non-capitalized cavity. Okay, so this means cavity is equal to true, and then not the opposite case. Probability of cavity being false is used with the not symbol. You are familiar with that symbol, right? Okay, good. Okay, now we can, we can introduce priors or unconditional probabilities. And these correspond to basic beliefs that you have prior to the arrival of any other evidence. So something that you believe, right, to be the case. So you decide that your prior for arriving at the airport in time, if you leave 60 minutes before, is like with probability 0.5. It's something that you decide, maybe based on some historical data that you have seen, but it's something that is not based on new information that you're collecting. So it's not that you have seen the fact that there is traffic. So this is something independent of any evidence that you have of the world. Something else that we're interested in are joint probability distributions that for discrete cases can be represented as a table. So if we have, in this case, two random variables, which are weather and cavity, we list all the possible values for weather, all the possible values for cavity. We list for each of those the probability of their combination. And this is our joint probability distribution. Now, what is the probability of weather and cavity is actually the multiplication of the product of the probability of weather and the probability of cavity, because they are independent. Now we'll see better what it means to be independent. So we have seen priors, we have seen joint probabilities. We have, in addition to these, conditional probabilities that are also called posteriors, which is actually something very common in the naming that you will find in most of your path from now on in this corso di laurea, in this master degree, is the posterior term. And this corresponds to belief, to some belief after you have some evidence. So now what is my belief that I will arrive in time at the airport after seeing that there is so much traffic? Okay, so there is some evidence that changes my view of this probability. So now here I listed a few examples. So if I know that I have a toothache, then the probability of a cavity is probably higher, right? And if I know for sure, so if I'm conditioning my probability of cavity based on the fact that I have a cavity, so my evidence is that I have a cavity, then the probability is 1, right? There is no doubt about that because I have evidence about the fact that I have a cavity. And again, here, probability of cavity given toothache and wind crashes, so the fact that window crashes is, these are unrelated. So my probability of having a cavity is just related to toothache. I can just remove the other variable. Because they are independent. So what does it mean in practice to be independent? So two random variables A and B are independent if and only if the probability of A given B is the same as only the probability of A. Okay, and vice versa. The probability of B given A is equal to the probability of B alone, or other thing, the probability of A and B is just the product of the two probabilities. Okay. What does it happen now if the two probabilities are not independent? So we have seen that the probability of A and B, so the joint probability, this is probability of A and B, is also called joint probability as we have seen before. So probability of A and B, in this case, is the product of the two. What if A and B are not independent? Then in this case, the probability of A and B is equal to the probability of A given B. A given B means the probability of A based on some information on B, multiplied by probability of B, which is the prior on B, okay? So again, to rename these things, the joint probability of A and B is equal to the posterior of A given B multiplied by the prior of B, or you can invert the two, and the posterior of B given A multiplied by the prior on A. Now you can see that given this formula, we can also compute the probability of A given B as the joint probability of the two divided by the probability of the condition of the evidence. Okay. Of course, this based on the fact that probability of B is not zero, so the prior on B is not zero. You can apply this in a recursive way. And so by applying this formula several ways, you obtain the chain rule. You can look at the formulas at home if you don't remember exactly now. That is not the important thing. We want to refresh your mind with the concepts. Then the formulas you can look at home. Some more examples. So what if we want to do some inference based on a joint probability distribution? So we have a joint probability distribution that is represented in that table. The joint probability distribution is on 3 random variables, which are cavity, catch, and toothache. And now we want to know what is the probability of toothache. What do? We just sum all the values that belong to this part of the table. Easy. Another okay. I don't know why they are switched, but it's fine. I want to do this first. Okay. So now, what is the probability of not having a cavity given the fact that you have a toothache? It's just the probability of not having a cavity and toothache. What is? It's this green part, right? Because you need to take this area of the table, probability of toothache, and intersect that with probability of not cavity. So this is the box that we care about, and probability of toothache is the same as before. So now you can do your computation by just summing and dividing these numbers. Here, we used something that we have just seen, which is the formula that we have seen here based on the product rule, okay? Here I have one more example, but I think you can see these at home. It's not really important. You got the concept. We don't want to focus too much on the on the numbers here. Then if you have questions or doubts, again, you can always send an email or ask for office hours, which I want to repeat that are on Thursday. I don't remember the exact hours now. They're written on the website anyway. Okay, so something very, very important now, which is basically what we're going to use for the next 3 lessons is bias rule. So what is bias rule? Is just rewriting things from the product rule, right? So the probability of A and B, we say it is equal to the probability of A given B multiplied by the prior of B, and or also to the probability of B given A multiplied by the prior on A. So given this, we can compute the probability of A given B as the product of the probability of B given A and the prior on A divided by the prior on B. And we just took the term, right, probability of A given B multiplied by prior of B. We divided by probability of B, and we got this formula. So now what do we have here? So this is our posterior probability, right? So this is a posterior probability of some hypothesis given some evidence, okay? And this can be computed basically by multiplying the likelihood of the evidence given some hypothesis with the prior of that hypothesis that you choose basically, divided by the marginal. The marginal is nothing else than the probability of the new evidence under all the possible hypotheses. So you sum over all the possible hypotheses and you get the probability of the evidence. Okay? Now, some other important things that we need to refresh in your mind is expectation. What is the expectation? So the expected value is nothing else than a weighted sum of some values where the weights are the probabilities. So for example, in a for discrete random variable with values from x1 to xn, then and probabilities p1, pn, then the expected value of that random variable is just the multiplication of each individual value by its own probability and the sum of all of that. Now, if you switch to a continuous random variable, then we just have to replace the sum with an integral and the discrete probability value with a probability density function. So what is this expected value? It's nothing else than the mean, the mean outcome that you can get from a random variable. It's the average outcome of a random variable. So when you say that the random variable in expectation has a certain value, that means that that's the mean, the average error, the average value that you get. There are some probabilities, some properties here that I listed. We're not going to see them here. I listed in this slide just for you to say these are important. Please, if you don't remember them, go back to your probability books and look at those, okay? Now, other important things here are the variance and the covariance. So the variance is the expectation of the random variable from which we subtract the mean and we square this thing. So basically how it's going to change this random variable if we are going to remove the mean value, right? It's representing the variability of this random variable. There are also here some properties that you will see at home. And the covariance is basically the same idea of the variance, except the fact that we're not using the same random variable. We are computing how one random variable is related to another one somehow. How one random variable changes in phase of another one changing too. Okay? So now some common distributions that you might want to look at are these ones. I recommend for you to look at least at 3 or 4 of these, which are the uniform probability distribution, the normal, which I have a couple of slides on here, gamma and beta that are related to the normal distribution. You can look at those because these are a common one, and also the exponential one. So these are the one that you should focus on in The other one are not really occurring throughout this course at least. But the ones that I've mentioned, yes. So here I put a couple of slides on the normal distribution because this is, together with the uniform distribution, the most important one that we'll see in our course being used. So the normal distribution uh, basically turns out to be something like the lines that we have plotted there. And this has some values that are relevant for us that characterize the distribution itself. So in order to represent this probability distribution, you need two things, which are the mean and the standard deviation. So the standard deviation is just the square root of the variance. Okay? So, so the mean is the expectation, as we said before. And so if we change the mean, we are moving this plot to the left or to the right. So you can see that the green line has a mean -2 and it's shifted to the left. And instead, if we increase the variance or the standard deviation, we're just flattening the curve, okay? Now, this is the one-dimensional case. Typically, normal distributions are called multidimensional or multivariate Gaussian distributions, and they can be multidimensional. And I mean, this is how you represent those. Again, you have the mean, and now you replace the sigma with the covariance matrix, okay? So now you work on here in this plot, we have two dimensions that we are focusing on. This slide is a bit scary, but please look carefully at it at home, because basically it's telling you how to compute conditional probabilities with Gaussians, where you are conditioning on, so we say this is a, we say that this is, when it switches, okay, we say that this is a bidimensional Gaussian. This means that there are two independent parameters. Now, what happens if we want to get the probability of one of these two parameters conditioned on the other? Then in order to get that, you use one of these formulas here, okay? So you can, again, you can look at this at home. It's just something for you to know and have fresh in your mind when we'll need to use those. If you want to go deeper, at least on this slide to understand it better, there is a paper that I've mentioned here that I think I will upload also on Classroom, which is how showing you how to manipulate multivariate Gaussians. Now, this said, let's see if there are questions. And okay, so we can't hear Zoom anymore. Video covers your voice. We already got this, and we already got this before. This is fine. This is fine. Fine. There's no audio on Zoom. Okay. Could you spend some more time on these topics? Which topic? Can you? This is a bit generic. Which topic specifically? And I can't do a whole probability course here. Sure. So maybe the correct way to do this is, if you think you are not solid enough on this topics, you can, let me think. So what I will do is I will create a poll on Classroom, and asking you whether you need some further explanations. If we get some, I mean, a decent amount of people that need to go deeper in this topic, I will cover it in at the beginning of the next offline video that I will record for the next class. So this is what I can do. But again, there needs to be a critical mass. Otherwise, you should get back to your books and do it yourself. I can't cover everything that has not been done in prior courses. This is, I mean, it's at least the minimum expected knowledge that you should have for this master and for this course. But sure, again, if there is critical mass, I will try to go deeper in some topic. Other questions? Here, is there? So let's wait a couple of minutes more. Again, I'm sorry for the start that was so difficult, but it's the first time that we use all of this machinery. And it's also hard to figure out here which computer I should use for something. So let me see, because maybe I can create a poll directly here, at least on understanding whether there is critical mass. So, aggiungi una domanda. All right, sure. What's wrong here? It's fine. I will do it on Classroom. It's easier. Never mind. Okay. I don't see any other question on Slido, so I'm assuming we are fine for now. And thanks for attending this class. I hope you got excited about the topic, despite seeing all this probability stuff that you'll need to know. That's why I tried to show all the videos before, so it didn't get too scary. Okay, if we're fine, we can close this class. Thanks. Stop the share here. So let me stop the streaming first.